It's 14 hours.
Oh, okay. Okay, so should we start? So it's my great pleasure to introduce Dr. Akitada Sakurai from Okinawa Institute of Science and Technology. Dr. Sakurai did his bachelor's in mechanical engineering at Meiji University in Tokyo. Then after that, he did his master's in physics at the Tokyo Institute of Technology. And his PhD was at the National Institute of Informatics in Tokyo, which is the premier institute for information sciences in Japan. And what is remarkable is that he got the best thesis prize for all of these 3 degrees. And his work for his master's thesis, which was on CP violation in atoms to probe new physics beyond the standard model, still continues to be one of the best in that field. And I know that for a fact because I was his master's thesis supervisor. And then he went on to do his PhD at the National Institute of Informatics, where he did groundbreaking work on time crystal, the subject of his talk today, and quantum machine learning. He's going to talk about quantum machine learning this Thursday. And he's been a postdoc at Okinawa Institute for Science and Technology for a year, and he continues to do work of the highest quality. So with these few words, let me now welcome Dr. Sakurai. Oh, you have.
Thank you for that introduction. I'm very happy to get a chance to talk today. So today we talk about let me check. Yeah, it's one. Yeah, fortunately it doesn't. Okay. Okay, now it's one. Okay. Okay, today I would like to talk about my old research, my PhD project on the time crystal on the network. And this is the outline of my talk, today's talk, and this has three components. So first, I will talk about the introduction and briefly explain the symmetry breaking and time crystal, what is time crystal, and what is the discrete time crystal. And then I will talk about my project. First one is the cumulative time crystalline order in spin network. Then I will talk about this is the second topic, time crystal growth for the spin network. So what is the symmetry? The quantum mechanics. So in the quantum mechanics, symmetry is some operations under the which system is invariant. Okay. So this is the Hamiltonian. I think all of people know this one. It determines dynamics. And this is the operator, symmetry operator. And the symmetry operator is to commute with Hamiltonian. And it means that the Hamiltonian is invariant under the symmetry operation. And symmetry is essentially the quantum physics. And also it helps us to understand the physics. For example, atomic physics or molecular physics, they are rotational symmetry, and it helps us to understand the structure of atoms or molecules, for example, orbits, 1s, 2s, 2p, something like that. Or in relativistic theory, they are Lorentz invariant, which also helps to understand the physics of relativistic theory. For particle field, there are so many symmetries, gauge symmetry, GPT symmetry, and actually these other professors that say it's my master thesis work is on this area. But today I would like to talk about the quantum phase of matter, and in this area, not symmetry, but symmetry breaking plays an important role to understand the quantum phase of matter. So to understand other example of the quantum, symmetry breaking, I would like to use some simple models. So let us assume the Hamiltonian given like this. This is a very simple Hamiltonian. It has only Z interactions and the transverse magnetic field. And this Hamiltonian invariance under the Z at Ising symmetry or parity symmetry under this transformation. And it's easy to check because this becomes minus, it becomes minus, and minus minus is plus, so it cancels out, and it doesn't affect by these transformations. Now, what is the ground state of this Hamiltonian? For example, when the transverse magnetic field strength is much larger than the strength of interaction, then its ground state is almost like this one. I don't know how many people are familiar with this symbol. RL and it means that almost eigenstate or sigma x or transverse magnetic field. But it's an invariance under the parity or Z to Ising symmetry. It has same symmetry of Hamiltonian. And it's called the ferromagnetic phase in macroscopic point of view. On the other hand, when strength of interaction is much bigger than the strength of transverse magnetic field, its ground state is either the all spin up or spin down. And at the thermodynamics limit, either this state or this state is realized. It means that, and this state is not symmetric under this symmetry transformations. It breaks symmetry, and this is called the symmetry breaking state. Now, I would like to talk about time crystal. So, Professor Wilczek, he got Nobel Prize. I don't remember the topic, but yeah. Okay. And he proposed a new phase of matter breaking a continuous translational symmetry along the temporal axis as another to the crystalline order. So in crystal case, for example, if we imagine the Hamiltonian, which is invariant under the space translational symmetry, and we know the crystal, which has some observable, which show the periodic, nice periodic oscillation along x-axis, and it breaks the symmetry of the Hamiltonian. And similarly, Wilczek proposed that it might be possible to consider the system, which is the system Hamiltonian is invariant under the time translational symmetry breaking. However, its observable or state is the time periodic function. It breaks the symmetry of the time. And his motivation is also coming from the relativistic theory, because in the relativistic theory, the time and space is equivalent. But unfortunately, soon, Professor Watanabe and other people show that it's impossible to realize the continuous time crystal as a thermal equivalent state. In short, briefly say, at zero temperature, the ground state is realized, and the expression value of ground state should be time periodic if we follow his idea. But as you know, that generally ground state is not time dependent. Or when in the finite temperature case, the expression value is gives some equivalent state given by this, and it is also not time dependent. Now, actually, the Professor Watanabe paper gives a strict physical definition of time continuous time symmetry breaking, because this explanation is not good to explain the why continuous time crystal does not exist at the thermal time activity. These conditions also doesn't work to explain the normal crystal. So that's Watanabe's paper. He also gives a more precise definition of time crystals and more mathematical proof he shown in the paper. But there is still a possibility in the non-equivalent state, because his proof is only considered about thermal equivalent state, and it's not included in the non-equivalent system. And later, Dominic Ellis expand the idea of time translational symmetry breaking and time crystal to the Floquet system. So he proposed that the discrete time translational symmetry breaking in this proposal, he considered time periodic Hamiltonian like this one. It's the H t plus capital digit period is the HT, and sometimes people call it the Floquet system. And if the discrete time translational symmetry is broken, then there are some physical observable which show the periodic oscillation with different periods of Hamiltonian. That's why n equals not 1, like a 2 or 3 or 4. For example, here I'm showing the sketch. So, for example, the middle green line shows the periodicity of Hamiltonian. Its period is T. But we expect that if the systems or states break the discrete time translational symmetry, then there's some observable, like a red line, which period is 2T now. And one of the example of the 2T discrete time crystal is represented by here. So it has 2 parts. From 0 to T1, we applied some rotation. And generally, G equals to T1 equals to, but it means that it's a spin rotation, the flip. And with some error, it should represent the error. And we have many body interactions and disorder in the second part. And this is applied from T1 to T. And in original model, people consider the interaction is long-range interactions like this one. And this disorder is necessary to avoid thermalization. But today I think I don't have time to explain what is the thermalization problem in the Floquet system. So I want to skip this part. But if you want to understand, please ask. Now, let me explain why we need this interaction is necessary, or why we can call this model is the phase. So first, let me show the result of the absence of the interaction. If there's no interactions between the net spin, sorry, this is a spin model, like a spin net, like a QB and interact with each other. And here I'm showing the magnetization dynamics of magnetization, local magnetizations for different periods, and you can see that it's not synchronized, right? they have some periodic oscillations, but it's periodic. It looks like 2T, but it's not synchronized yet. But, and here I choose a epsilon equal to 0.01, 0.01, very small, but once we turn on the interactions, now you see that all magnetizations are synchronized well. And we call this is a time crystal because it's very robust against the error in the rotation. I say that it's the first part represents the flip. So if epsilon equals 0, it's obvious that right we need a 2 period to get the same position, like a magnetization go back to the same position. It's obvious. But now we have an error. But even if there is the error in the rotation, it still have a nice oscillations, the dynamics. Now I would like to show the phase transition of this system. So here I'm showing the dynamics of total magnetization. So this is total magnetizations, not local one, up to for different value of error. So up to 0.07, we can still see the nice periodic oscillation. And we can call this the 2T DTC phase or DTC phase. On the other hand, if the epsilon goes increase more, like 0.09 or the 11, 13, then periodicity it vanishes. It's not like a periodic oscillation anymore. And this phase is sometimes called the MBL phase or thermal phase. It depends on the case. Now, this is the introduction part. Now I would like to talk about my doctor project on CQuERE discrete time crystal or CQuERE time crystalline order. And it's the this result I will show you today is also published in the PRL in 2021. So what is the CQuERE? Before I talking about my project, I would like to briefly explain what is the CQuERE. So CQuERE is originally from Greek mythology. So CQuERE is a beast, which has the head is the lion and the goat, and its snake. Its tail is a snake, like this one. And in physics, in classical mechanics, nonlinear dynamics, Kuramoto proposed some systems as a nonlinear system, and he showed that it's like a pendulum with a nonlinear interaction. And he found that if you plot the phase of pendulum, they are synchronized phase and unsynchronized phase coexist in the same system. And he called it the CQuERE state in the classical system. And similarly, in the semi-classical regime, my colleagues, Victor Basilias, proposed some model, and this is the semi-classical model, and he puts nonlinear terms in the classical quantum system, and he also showed that in this model, they are synchronous and unsynchronous phase coexist in the same system, like here. But in true free quantum mechanics regime, it's a bit difficult because Schrödinger equation is a linear function, a linear equation, why like this one. And generally, quantum state is very completely entangled or scrambled by interactions by the quantum variable system. And from these reasons, it's unclear whether stable CQuERE state can exist in the quantum system. But maybe it's possible using the driving force like a time crystal. That is my work. So we propose we expand the original time crystal model like this one. We divide the systems into the network into two parts called region A and region B. And we consider the different errors. And for example, if epsilon A is an error in the region A, because they're very small, and if we choose error in B, it's large. like this, this part. Or sorry, this the not 2D. In the actual calculation, we consider only one dimension. Yeah? So now we, as is showing here, we get the from 0 to 3 qubit. They shows some nice periodic oscillation like a time crystal, but this part is not time crystal anymore. It's a ferromagnetic state. And the interesting point is because our original Hamiltonian has an interaction between each system, and it is actually long-range interaction. So two net regions are strongly coupled via interactions. Otherwise, nevertheless, they show the nice two phases coexist stably. And here I'm showing the right side, I'm showing the cumulative DTC for long period. And up to 10,000 period, two states coexist stably. So why two different phases coexist stably? To understand the detail of this mechanism, we look at the state information. And to get the information of the state, we use Neumann entropy. I don't know how many people are familiar with Neumann entropy. You know these notations, so we trace out that a part of regions, and it tells us how much these regions are entangled each other. So this is the closed system. Now I'm here. I'm showing the two different cases. So first, blue dot show the DTC case, epsilon A equal to epsilon B case. And I choose epsilon A equal to epsilon B equal to 0.01. It's normal DCC. And we see that in this region, the entanglement, Neumann entropy increases with time. And it means that it's, as a result, two regions are synchronous, like this one. Here I'm showing the magnetized dynamics for different period and for both regions, and they are almost the same, right? Can you see the blue and the red? So it might be difficult. It looks like purple, but anyway. On the other hand, in the time crystal, cumulative time crystal case, I mean the epsilon A equals not equal to epsilon B. Its entropy is highly separated in the time. It doesn't increase. And it means that two systems or two regions, it looks like separable. They don't talk each other despite their interaction. So from this result, we see that okay, two regions is separable, and as I said, and but we have interaction, right? So what did happen? So to understand that, let us look at the effective Hamiltonian for 2D. And I'm not sure how many people are familiar with the Crooked system. That's why I put this slide yesterday. So the original time Hamiltonian is the time dependent, like this one. But and dynamics is like a function of t. But we are interested in the only dynamics at the stroboscopic point, like every t. That so first we calculate unitary for one period, and it is called the Crooked operator. Sometimes people use F as a symbol, and it can be expanded or can be written in terms of exponential form, like this one. And this Hamiltonian is called effective Hamiltonian. So this effective Hamiltonian determines the dynamics at the stroboscopic time. And especially in the time crystal case, we are interested in the only 2t point, 2t period. That's instead of effective Hamiltonian, let's look at the effective Hamiltonian for 2t. It's gamma dynamics at every 2t period, like a red point. Now, we analytically derived the 2t effective Hamiltonian for 2t. So first, for simple case, if epsilon A equals to 0 case, and epsilon B, in here, I assume that epsilon B equals to 1. We got this one. So you see that there are 3 terms, and this is the interaction term, but there is no interaction term between 2 regions, because this interaction is only spin in region A, and this term is represent interaction in only region B, and this is disorder in region B. And interestingly, there is no disorder. Disorder is also disappear in region A. Now, so in epsilon equals to 0 case, 2 regions are completely decoupled. And both region A and B has a U1 symmetry, and region A has a Z-leading symmetry, parity symmetry. But region B doesn't have it because we have a disorder. And next, when epsilon A equals non-zero case, but it's very small case, we got this one. And important point is that the original interaction is scale with the J. It's the length of the interaction between 2 regions, the determinant of the J. But now, interaction between 2 regions is proportional only epsilon A. And that's why the 2 interact, we conclude that the interaction between 2 regions is strongly or highly suppressed due to the driving, the partial drive. So this is the conclusion of the first part. So we found a quantum chimeral state in empirically driven system on the network, spin network, will governed by the quantum mechanics. In our model, the DTC phase and the ferromagnetic phase coexist in the same system, and 2 quantum phases coexist stable despite interaction over the full network. Now we would like to talk about the dephasing induced time crystal. This is also published. The result I will show you today. I put it in the archive. Also, you can find my paper, physical level B, published in 2021. So now back to the original time crystal model again. So this is the original time crystal model. So they have a 2 steps, and now this is focus on the interaction again. So this interaction, sorry, I don't know why. Okay. The interaction helps to stabilize the thermal dynamics of the magnetization. And the property of this interaction is U1 symmetry. And it's related to the conservation of the magnetizations. And there are 2 types of U1 symmetry. The first one is a local U1 symmetry, like this one. And as a result, the local magnetizations are conserved. And on the other one is a global U1 symmetry. And this global U1 symmetry leads to the conservations of the local global magnetization. And now, this original Hamiltonian or time crystal, the interaction has both symmetries. Now the question is, so do DTC need to have both U1 symmetry to stably exist? I mean, do we need a local symmetry? That we propose a new time crystal. We replace the Z-delta interaction part to the XY interaction. Now this interaction breaks the local U1 symmetry, but has a global one. Now the local U1 symmetry is not local magnetization is not a conserved quantity anymore, but still global magnetization is a conserved quantity. How much time do you have? You don't have it. Now, let's see the dynamics of this model. So we prepare the initial state, the normal time crystals initial state, like a parity symmetry, parity symmetric state, like all spin up. And here I'm showing the dynamics of local magnetization. And you see that despite it doesn't conserve the local magnetization, it's still nice periodicity that appears. So it means that to get time crystal line order, we don't need, the system does not need to have local U1 symmetry. But now, is there any essential phenomena due to the local symmetry breaking in the Hamiltonian? To get the more interesting dynamics, we consider the new initial state. So dynamics of DTC are affected by both symmetry of the state and the initial state. For example, to get the DTC phase, as I said, initial state, it should be break the parity symmetry, like this one. On the other hand, if initial state has a parity symmetry, like this one, we cannot get the DTC state. So we consider the hybrid of these states. So we consider new initial state where the half is a spin parity breaking state and half is the parity preserving state, like this one. So what will happen to the dynamics? What's the dynamics of this new initial state? Now here I'm showing the dynamics of new initial state. So our new initial state is half is up and half is the parity preserving state. And horizontal axis is the period, right? So you see that this part shows the magnetization, and here I'm showing the local magnetization and color means the amplitude of magnetizations. White means 0 because we choose this state, initial state of iteration, and red means the maximum number amount of the local magnetization because we choose the this state as this one. Now the time increases, we see that it grows for the magnetization, right? And we call it the crystal growth because crystal the time something like a time periodicity growth, and it's like a growth of crystal. But the problem is because due to the boundary effect and interference, they cannot reach a stable time crystal even we wait longer. But however, we can separate these effects using the environment effect. So we expand our model into the open system. So in general, in DTC, summarizations destroy the quantum phase as similar to that of DT phase of matter. And DTC in the existing spin models do not stabilize due to the effect of environment effect. So, but we have two fundamental questions for DTC. With environment, is it possible to consider the system, including the DTC model and environment, and with its entire system should preserve the U1 symmetry? And can symmetry of the total system helps to stabilize the DTC behavior? And one possibility is the defading. So we consider the DTC model with defading effect. I'm not sure how many people know the defading, but I don't have a slide to explain the detail of defading. So now, here I'm showing a result of local magnetization without defading. So I want to say again, so oscillations are not synchronized yet. But now, by turning on the defading effect, you see that the local magnetization is synchronized. It means that the defading effect helps the system to stabilize the DTC phase behavior. And now we want to know that how long does it take to be stabilized, which means that we want to know the time scale of the crystal growth. And please remember that it's about 50 periods, right? Among this period, so it's like roughly 50 periods. So it is possible to estimate the time scale of crystal growth. So for that, we focus on the Rivilian gap. So first, this is the equation of motion of the open system. And this here, the rho is the density matrix, and it's the Rivilian operator. Okay. What? Now, as similar to the dynamics of a state, it can be expanded in terms of eigenstate or Rivilian operator, and puts the phase, and this lambda is the eigenvalue over the Rivilian operator. And the first term is called steady state. In general, steady state should be 1 in general. But our system is a periodic system, so we expand this. We have to expand consider the similar approach in the Floquet system. In the Floquet system, also we can expand the dynamic, the density matrix, dynamic of density matrix at the through-specific time with covered by by the steady state of Liouville operator and the other eigenstate of Liouville operator and the eigenvalue of the Liouville operator like this one. And now this part represents the stroboscopic steady state. Doesn't okay. Oh. Oh. No, not this. Ah, two things. I okay. Okay, no problem. It's cool. Okay. So now, Liouville gap. What's the Liouville gap? So to okay. So we plot the eigenvalue of the Liouville operator as here. Because the Liouville operator, eigenvalue of Liouville operator is a complex number. And imaginary part is coming from the quantum dynamics. And real part is related to the say environment effect. And here we plot the Liouville eigenvalue of Liouville operator, Liouville eigenvalues in complex space. And this point it represents the steady state. And this point is represent the first Liouville non-zero eigenvalue of Liouville operator, and we call this part the Liouville gap. And generally it's proportional to gamma t. Gamma is the strength of the phase. And it tells us the scale, time scale of the relactizations of the system. And we found that in this model, Liouville gap tells us the time scale of the DTC growth. And we actually calculated the Liouville gap and we get 50. And it's very much almost same as we expected from here. I think almost 50 period need to get to for the DTC growth. Yeah, sorry, this is the conclusion of my talk. So we found that the 2D DTC phase on spin network with X or XY interaction, preserving the global Riemann symmetry, but breaking the local Riemann symmetry. And due to the local symmetry breaking, the network, the new spin network shows the discrete-time crystal growth, which does not exist in the conventional model. And we found that the dephasing effect plays an essential role in the stabilizing the crystal growth in our model. That's all. Yeah, sorry, this is the conclusions.
So any question? Wait.
So what kind of interactions do you consider with the environment? So
Yeah. I don't like because I didn't have time to prepare the slide, so maybe I don't. Is it possible to access the internet? Possible to open the my okay. Sorry, I don't have a slide, so can I use my paper? Oh, okay, let's see. Okay. I'm not sure how much you are familiar with the open system. So in our actual calculations, this is the Hamiltonian, and I explained that. So, and this is the Euclidean equation, which represents dynamics of open system. And now here, this is the inside of the details of this part. So it has a quantum dynamics part. We call it coherent dynamics and decoherent dynamics. And interaction term is not, it doesn't represent interaction, but I can say that there's a sigma delta interaction. Because dephasing means usually means that we map, the block sphere.
Yeah.
So the spin is projected to the z-axis due to the this interaction.
So my question was this: gamma is always greater than is equal to 0. Like I'm asking if you're considering only Markovian interaction.
Markovian, non-Markovian. Sorry, Markovian. I think it's Markovian.
Yeah. So okay, you didn't consider non-Markovian interactions.
Yeah, so far, yes. It's only Markovian effect.
Okay. Like from my understanding, I think if it might get some interesting results if you consider non-Markovian, if
Yeah,
possible.
I expand this model to the non-Markovian case, but when we consider time crystal growth, there's no reason why we need to choose the non-Markovian. We want to show that it's possible to stabilize, DDG growth can be stabilized using the environment effect. That's our main purpose. So we don't, there's no reason, right?
Okay.
So we choose a very simple scale, for example. Oh, sorry.
My question is, even in classical system, you have broken continuous symmetries.
Yes, yes.
Right.
In the,
So it doesn't have to be always quantum to have this. So my question is, what is special in this situation that's different from classical notion of broken symmetry? For example, I mean, is there an equivalent of a Noether's theorem here?
No.
Or because you are not in equilibrium, that doesn't work? Or
actually, some of people try to find a time crystal phase in classical system, but so far it doesn't work well. And the problem is because classical system is more phase of matter in classical system is more restricted, right? It's I mean, they have to follow the thermodynamics in classical system case. And as I said in the talk, in thermodynamic limit or in the thermal equivalent state, it's difficult to get the time crystal order proved by the Watanabe.
okay, so maybe I didn't state it quite correctly. So my question is that in a quantum system, are you saying that you don't have to worry about thermodynamics because you are at t equal to 0, or?
Not that, of course, I mean, in both cases, quantum and classical, it's impossible to get a continuous time translational symmetry breaking or continuous time crystal order in equivalent system. So, but I'm not sure that in classical case, it's possible to make the time crystalline order in non-equivalent systems. But I'm not familiar with the
It
phase
is.
of matter in non-equivalent system in classical case.
If you drive it, you can. If you take it away, nonlinear systems do that.
Systems, for example, and some people propose that time crystalline, something like time crystalline order.
But sorry, one more question. So what do you mean by, you use the term stroboscopic times. So what does that imply? That means you look at it periodically? I mean,
yes, only focus on dynamics at certain period. I mean, the periodic.
and that period depends on something. Your Hamiltonian.
Yes, depends on my as shown here. Okay. This is the Hamiltonian of my system, and this is from 0 to T1, we apply rotation, and from T1 to T total T, we apply the interaction are shown this order. And this Hamiltonian is time periodic. And we are interested in dynamic at periodic time. So we don't care about the dynamics at the arbitrary times.
Thank you.
Thank you.
You have talked about the time scale for
Yeah.
the DTC growth, and you expressed it in terms of that number period, like 50. But what's the actual time scale? How fast I have to drive it? It's nanosecond or second, whatever. So the 50 means it's the number,
Number of period.
but the length of one period. So that should matter, right?
Yes, it depends on the in the practice, in experiment.
So in experimental, if I want to drive the spin, so how fast it has to be?
Good question. So I don't remember. We have calculated the actual time scale, but we try to propose this model. We invite some experimentalists and we discussed it. But I'm sorry, I don't remember the details. But for example, in trap ion case, it have shown that time crystal can be exist 100 period, and time is some nanosecond, 100 nanosecond or something like that. So it means that the one period is one nanosecond. Because they show that the time crystal can be produced in 100 period, and they say that 100 period equals 900 nanosecond or something. I don't remember. I don't remember. The relation time crystal comes like that. Observation of time crystal. Someone already check. Yeah. This is the first experiment of time crystal, realization of the time crystal with trap ion. And they showed that, remember the scale of I have checked the coherence time. Yes, coherence. I don't remember the time scale. Explain here. Microsecond. Wow. Nanosecond. Okay. 75 nanoseconds. This is a total number of periods. One period. They apply the pi rotation from for 50 microseconds. The interaction part is 27 microseconds. This other part is 30 microseconds. It's possible to perform on the
So the order of nanoseconds.
nanoseconds in trap ions.
Okay. So I have a little confusion once you have written the operator U, T, comma 0, and which contains, of course, the Hamiltonian on the right side. But I suppose it's an integration from 0 to t, right? So this
Yes.
is one period,
Yes,
but you are dealing with multiple periods.
yes.
So your integration should go from 0 to how many periods you are taking.
Yes, yes, yes. And but right, in the experiment case, I don't know if we can compare the integration, but in analytical case, we divide the system dynamics into two parts, and this is not integration, right? Because we apply by rotation first, from 0 to T1, create one unitary, and from T1 to T, this create another unitary. So total F equals to U1 times U2.
Okay.
Sorry, I think other people also. Sorry.
So I have two questions. So first you have started talking about Hamiltonian symmetry,
Mhm.
and then you are going to open quantum system.
Yes,
So do you need to talk about Liouvillean symmetry there?
yes, I talked about the even operator.
Yes, you talk about Liouvillean operator. You are showing the dissipative phase transition, but now we need to talk about Liouvillean symmetry. No more Hamiltonian symmetry. And second thing is that when synchronization is concerned, so we have a linear gain and non-linear damping or the vice versa case for the self-sustained motion. So if,
last part, but
because there should be some kind of gain in the system and there should be some damping also in the system. Without that, you cannot talk about synchronization.
it's not actually the synchronization.
But you are every time mentioning in terms of synchronization.
Synchronization. It seems like the all part is synchronized with same period, but the mechanism is different for the synchronization. Originally synchronization in the open system. I know the synchronization.
Yes.
But because we have driving force and
You have that is basically giving you the gain,
yes,
but there should be some kind of damping also to compensate the gain.
yeah, dephasing.
Dephasing. So that in the first slides you are showing there, there the dephasing part was there, or this is the first work you are considering dephasing here?
So
Means you presented two work, one is PRL and one from PRB. So in the PRL paper, you are considering any kind of dissipation or
error.
and in this paper, you are mostly talking about the lambda one part of the Liouvillean. So don't you need to talk about the imaginary part of the eigenvalues also, because you are doing the synchronization and the time periods are coming from the imaginary part or the energy part.
There are some not. I mean, how can I say?
That plot you show in the real and imaginary lambda, the Liouvillean gap is there, the red patch, I think, somewhere there. In your slides, maybe.
Oh yeah.
So you show some plot of Liouvillean gap. No, not this one. The real, yes, this one. The real lambda and imaginary lambda. So you're only talking about the Liouvillean gap.
Liouvillean gap.
So it's a dissipative phase transition kind of thing happening.
Yes, it only because it tells the time scale of the relaxation time.
But you were talking about some time symmetry. So do you need to talk about the imaginary part of the eigenvalues also? I want to mean that.
To understand the DTC phase, we have to focus on the imaginary part also.
Yes.
But in this talk, I want to know is time crystal growth, scale of crystal growth, not time crystal, right?
Yes.
So that's why we only focus on the Liouvillean gap. If we want to understand full dynamics of DTC model, like what kind of symmetry is necessary to get the DTC phase, of course, we have to look at all part. I mean, the imaginary part also should be considered.
That's why I'm asking. So the Hamiltonian symmetry now becomes the Liouvillean symmetry.
Yes.
So you have to take for the Liouvillean symmetry.
Yes, symmetry. But yes, and this model case, the phase is only done in the Hamiltonian part. So we first we focus on the symmetry of the Hamiltonian. Then we expand this model.
So what's the role of then this dephasing gamma?
As I say, to stabilize the dynamics of after the type crystal growth. Yeah, so
Stabilize means after that this oscillation will grow in amplitude or decrease in amplitude. What will happen? In stabilized motion means, or they will decay to some point.
yeah, in this case, but here I'm assuming epsilon is a 0 case, the ideal case. In this case, we found that the steady state is a multiple steady state. They reach the steady state at two different points, like this state and this.
But these
And-
all steady states are means no oscillation is there. It's a completely a single point in the state.
Yeah, here I'm showing a
So if
steady-
your rho 0 is 0, then you are reaching a steady state without any kind of oscillation.
Yes, yeah, no.
And if there is no oscillation, then there is no synchronization.
No. In general case, yes. For example, the equation, for example, equation motion is represented by this.
That's okay.
Then we have some single or multiple steady state. And once they reach the single steady state, then there's no dynamics anymore, right?
But your steady state is not oscillatory.
But our system is a periodic Crooked system. We found Crooked steady state.
But in your Liouvelian that picture, your lambda 0 is 0.
Lambda 0.
That means your steady state is not oscillatory.
Yes, but they are steady state, two steady state. It's not single steady state, two steady state.
But if there's two sides, then there can be some bifurcation kind of thing. So you're having more lambdas to be 0 with some imaginary part.
Why we need to have imaginary part?
So you are writing that CSS rho SS. So rho SS is corresponding to the lambda 0 eigenvalue.
Yes.
So if you are having a steady state, that means you are having a single lambda that is having 0 eigenvalue. After that, you are starting expanding the e to the power lambda t part.
But this eigenvalue is the generator. I mean, there are 2 points there. There's 2 points, not single steady state, two steady state.
Means there's a kind of bifurcation kind of thing or bistability kind of thing. No? Yes.
My question is somewhat related to his. So when you strobe it, you are showing these oscillations. Do they always appear in phase?
Appear in phase, but
That is, are they phase in? I mean, that is, you know, I can have periodicity, but I could have the next time I look, it's also periodic,
yes.
but it's not in phase synchronization with the previous look. Meaning that if I superimpose the pictures at the interval, synchronized interval, they will not overlap, but will be phase shifted. Are they phase shifted or?
They're not phase shifted. Yeah, it's completely.
Okay, so let's thank Dr. Sakurai again for the So he's here for the till I think the end of this week. He'll be giving a talk on Thursday on quantum machine learning, but so feel free to talk to him. Okay, so thanks. Thank you, Secretary.
Yeah.
Thank you.
Thank you. Yeah.
I visited it.
Yeah, maybe. Yeah. Oh, the postdoc. Yeah. I saw it.